Thank you all for coming to join me in this afternoon session. We're going to change gears from some of my earlier talks and talk about pollination. This is another one of my areas of research interest. And I've been working in pollination now for about 25 years on the research end, and there is definitely a sort of an anti-honeybee movement out there. And it happens not so much at the grower ranks, but very much so at the scientist ranks. There are, just a lot of opinions out there that in most of their modern range, the honeybee is non-native and therefore should be summarily extirpated from the habitats. I think that's misguided for many reasons, and my lecture today is going to be sort of making a scientific case why that is not really necessary. Though I do have to say I was corrected a month ago at one of my beekeeping institutes that I do in Young Harris College in North Georgia every spring, and I had a speaker from Penn State, Margarita Lopez Uribe, who was speaking on some of the ecological impacts of honeybees where it's been introduced. And there is evidence that it has competitively harmed some native bee species. But at least in agriculture, the honeybee pollinator is really the standard against which others are measured. It's not by any means a perfect pollinator, but it's pretty good for most crops. And I'm going to be talking this afternoon about some of the more recent data showing how that this relationship with other bee species is actually synergistic and favorable. So I think you'll find it interesting. And I'm going to kind of, once again, sort of a bigger picture view, look at some of the questions we ask when we're trying to decide who is a good pollinator for what crop. What does the question even mean, and how do we go about answering it? So this is about as big as the picture gets. This graph right here is showing the phylogeny of honeybees, some of which you saw abbreviated this morning on the chart, and I'm blowing open the part about bees itself. And this is about 120 million years ago, and you see wasps are the ancestral stock of the bees. We call these, whenever we're doing a phylogeny like this, where you have like a branching tree, kind of like a sports playoff tier in the brackets in the NCAA basketball tournament, for example, the opposing group is called the sister group. And so wasps are the sister group to the bees. They are the most recent ancestors, and wasps are the more primitive stock that bees branched off of. So this explains why to this day common lay folk mistake bees and wasps, right? They just lump them into the same thing because they do look alike, don't they? Well, this is why they look alike. They are sister groups to one another in phylogeny. Well, about 120 million years ago, an important event happened in biology, and that was the arrival of the angiosperms, the flowering plants. And wasps, just like bees, their successors, are both vegetarian. They eat nectar and they eat pollen, wasps do, but they're also primitive in that they eat, they're predators, they're carnivores. Wasps are carnivores. And bees are simply wasps who have abandoned a carnivorous diet in favor of a vegetarian diet. And they did this because of the availability of the angiosperms. So this green circle is when the angiosperms showed up, and it's no accident that that's exactly when bees showed up. So it is one of the most celebrated events of coevolution in biology, how the bees and the angiosperms show up at the same time. It was a positive synergy. The angiosperms were producing pollen, and these vegetarian wasps started visiting pollen for their protein, and it benefited the angiosperms because it spread the sperm around to other members of their species. And so it became adaptive for those angiosperms to kind of up the ante a little bit and secrete nectar as a further reward to these vegetarian wasps who were visiting them, so that they would encourage this behavior because it was beneficial to them. And that was kind of the beginning of a happy synergy, if you will. Now, this is a good point as any to interject that, evolution never stands still. It doesn't arrive and celebrate, yay, we've solved it forever. Things are always in motion. And one of the things that has happened is angiosperms are not exactly happy with this arrangement. Because think about it, it makes their range and their reproduction totally dependent on these vegetarian wasps, which we can now call bees. And so this is the beginning of sort of a race, an arms, or kind of a reverse arms race, if you will, where the angiosperms are trying to regain their independence. And this explains the evolution of self-fertility. An awful lot of crops do not require cross-pollination. They do just fine without it. The best example of this is soybean. Soybean's a crazy plant. It has a flower. It secretes nectar in some areas of the country. I don't know about Texas, but like in the Delta region of Mississippi and Tennessee, it's a major honey plant, soybean. So it has nectar, it has a flower, but by the time the flower opens, the flower has already self-pollinated itself. I mean, the business is done, which begs the question, why does it even bother? Well, it bothers because its behavior hasn't caught up with its evolution yet. So this is just an example of how slow evolution moves in time. The soybean no longer needs a pollinator, even though pollinators still increase its yield. Okay, we can get a baseline of soybean yield, but above that you can increase it even more with the action of pollinators. So what is acceptable in agriculture isn't necessarily acceptable for the plant. The plant just wants to reproduce. We are the ones that try to juice the system to get extraordinarily, unnaturally high reproductive capacity, i.e. seeds, that are wildly in excess of what the plant needs to simply reproduce. I don't apologize for that. That's just the story of agriculture. Whether it's plant husbandry or animal husbandry, that's what agriculture is. We are pushing the reproduction of our species beyond what they need to survive. But from this basic phylogeny, you see how, once again, it's this hierarchy, this radiation, groups branching off of groups. And we see that our apidae down here are the most derived of the honeybee groups. If you look, they're the most downstream. The most primitive stream are up here, the melitids, and then the halictids, coletids, megachilids. But then you get down here, apidae is the most derived of the bee families. It's the most recent branch off of the bee tree. And of course, our own beloved honeybees are included right here in the tribe Apinae. Now, these other little circles are just sort of freebies thrown in, just have nothing to do with my talk, but it's still kind of cool to talk about. These open circles right here is when eusociality arrived. It's where it first showed up. And we see that it arrived independently over here in the halictids. The halictids are the sweat bees, the little green metallic bees that you see sometimes. They too have some eusocial groups, but they evolved it independently. You see how it's two separate derivations, and they were independent of one another. That's what we call in evolution an independent event, where they're not related to one another. They just both achieved or solved the same problem independently. And other funny things happen. Here we have a case of eusociality being lost. The so-called oil bees of South America, these are the euglossines, and they are the pollinators of orchids. Those of you who grow orchids or like orchids, these oil collecting bees of the euglossinae are the primary pollinators of your orchids. And they used to be eusocial, and they have abandoned it and gone back to the solitary life. If any of you were at my second lecture, I was kind of talking about how perilous it is, how difficult it is to become eusocial. There's a lot of genetic disincentive to go down that route. And the euglossines are one of them that said, nah, it ain't worth it. We're going back to being solitary. But then you have the grand champions of all, complex eusocial Apinae. And there is where we have the honeybees. Now, incidentally, the melaponines, the stingless bees that I talked about this morning, they also are truly eusocial. So there's been a few groups in the bees that have got it and kept it. Curiously, whether they are social or whether they are solitary has a lot to do with the pollination efficacy of any particular bee. Back to the flower morphology. I teach entomology, and so I tell my students when I'm lecturing that this is pollination, going from this box to this one. You see that stigma there, the pistil, the style, the female part of the flower terminates in this sticky surface called the stigma, and a pollen grain lands on it. And something has to get the pollen there from the male parts, which are these stamens. Right here on this part. Most flowers tend to be hermaphroditic. They have both sexes housed in one flower. And those that are hermaphroditic, pollination is relatively easy because it's a much shorter distance. It's just a millimeter or two, right? Those plants who have, non-hermaphroditic flowers or imperfect flowers, they have to have pollen come from another flower. So the task of pollination is inherently more difficult for like a kiwi fruit. For example, kiwi fruits have male trees and female trees. And so you got to transport pollen, for meters instead of millimeters. So that right there can play into how difficult or easy a pollination of any particular crop is. But once that pollen grain lands on the stigma, then it begins growing this pollen tube, which goes down the length of the style into the ovary. It has 2 sets of sperm per pollen grain, and one pollinates the embryo, and the other pollinates another region of the ovule that turns into the starchy component of the seed. So I tell people it's the second sperm that we have to thank for bread and beer. If you like bread and beer to make that starch in the seed, it's that second sperm in the pollen that you want to celebrate. The other sperm just simply goes to fertilize the embryo and make the embryonic seed of the plant. Entomology ends right here. Once that pollen is deposited, it's a botanical problem. And I try to fob that off onto my plant colleagues because technically our job is done once we're right there. But that's a very important part. Pollination is a positive contributor to yield. Think about it, a lot of what we do in agriculture is a conservative measure. We apply a herbicide, we apply a fungicide or an insecticide to conserve losses. And pollination is one of those steps in the agro cycle in which we're increasing yield. You see the difference? So this is one of the reasons why pollination is such a strategic input. It's kind of like fertilizer. It's kind of like irrigation. It's one of those things that will actively increase yield. So it's an important fundamental to crop production in those angiosperms that we farm. The honeybee, of course, is the standard against which others are measured. For all the good reasons we've talked about, they're domesticable. They are amenable to human management. They are mechanized. We know how to raise them in spite of all the laments that we talk about how hard it is to keep bees nowadays. We basically know how to rear them en masse at industrial scale. And we can ship them in, palletize them mechanically. There is no other pollinator that is this manageable, this fast. But there are other pollinators that have been marshaled into agriculture that are efficient and can't be overlooked. One of these is the bumblebees. When it comes to greenhouses, you can't beat bumblebees, just hands down. They're so far ahead of number 2 that I don't even know what number 2 is. The reason is bumblebees, they forage normally. You put them in a greenhouse and they don't wake up the next morning and freak out and bump against the glass all day long like honeybees do. The bumblebees come out and they say, oh, okay, the horizon looks a little different. Oh, wait, no problem. And they just fly over to the nearest tomato plant and back just like normal. So, go figure. I don't know why. They just do. So bumblebee culture is very different from honeybee culture. You don't rent them, you buy them. And so the companies produce these. They're not even made to be opened. The grower just simply pulls this little tab and opens them up so they can fly, and they're done. Some of them now are even in biodegradable boxes where you don't even need to pick them up at the end of the year. Just plow them under. And so it's a very different type of pollination. But you can't beat them in greenhouses. They forage normally, and they're very efficacious pollinators. There's other managed bees that are solitary, truly solitary. And probably the best of these is the mason, the alfalfa leafcutter bees of the upper states and the prairies. They use these at commercial scale to pollinate alfalfa. And alfalfa is an exotic plant. It's from Asia. The alfalfa leaf-cutting bee is its native pollinator from Asia. Both of them were imported. The alfalfa was imported intentionally. The alfalfa leaf-cutting bee accidentally. It was not intentionally imported, but it got in somehow anyway, and it has now flourished in those areas where they grow alfalfa seed, and they've now used them. They got their methods customizable and figured out. There are these little nest boxes that are perforated with nesting holes, and the bees fly and make their nests and collect pollen balls and pollinate the alfalfa crop in the process. Mason bees are kind of in the ascendant. They too can be managed to some degree, but at no scale approaching the alfalfa leafcutter bees. The alfalfa leafcutter bees and bumblebees and honeybees are really the three most manageable pollinators at industrial scales. Though there's a lot to be said for these mason bees, they are fantastic pollinators of all of the Rosaceae, which includes the apples and the cherries and the pears and the cherries and the plums. All those orchard trees. If you have to guess on the exam, say Rosaceae, and you probably got their family right. But these guys are fantastic pollinators. In fact, I read a stupid number. It's too good to be true. But there's actually a published value for these mason bees in apple that 3 female bees, 3 insects, 1, 2, 3 female orchard mason bees can pollinate an entire apple tree for its entire season. So that's an amazing degree of efficiency with these little mason bees. The trouble is with them, the alfalfa leafcutter bees, I showed you in alfalfa, they do a really good job of flying out, coming back, and stocking their little styrofoam holes that you give them. These guys don't. You stick them out, and they might just fly to the 4 winds, and you'll never see them again. So, again, behavior of the pollinator plays into their efficacy as a pollinator. You begin to see why honeybees are kind of the standard. You know, we know what they're going to do. You know, so that's kind of why we keep defaulting to the honeybee. It's manageability. But these solitaries, the reason they're so compelling is their efficiency. It goes back to their evolutionary history. Okay, here's what a solitary bee nest kind of looks like. Most of them are subterranean soil nesters. Some of them burrow into solid wood. Some of them occupy existing twigs, hollow canes or twigs. But this pattern is rather habitual and repeatable. They will dig a tunnel off of which there are lateral tunnels, and at each one of them they give a little ball of pollen and lay an egg on it. And then the female buries it with dirt or packs it with leaf material or whatever that species does, and they never give them any more parental care. And the brood develop. Some species are 1 generation a year, some are 2. 1 or 2 kind of tends to be the norm. And so there is a frenzy of activity once they do emerge, and that is when all of the mating is happening, the mating and the nest provisioning. So if I am a solitary species, it is very important to my survival that I encourage, that I propagate, that I facilitate, that I help those plants that are blooming at the same time, for crying out loud. You know, if they were there for me when I was active, then I should be a really good pollinator so that that same plant species will be around next season for my offspring, and so on and so forth. So this is why we get such extraordinary efficacy in solitary bees. And when I mean efficacy, it's like here's the poster child. The standard measure of efficacy is what is the likelihood that you can set the fruit with one visit. In fact, that's what we call it, single visit fruit set. And we can compare apples to apples that way. You can compare a bumblebee to an orchard mason bee to a honeybee. If it makes one visit to a flower, what's the likelihood that that flower sets fruit? How do you do this? Well, you go out in the orchard when they're still virgin flowers and you bag them, and then you don't, your graduate students do. They come back, they unbag the flower, and then they sit there and wait. And you wait and wait and wait and wait. Eventually, here comes bee XYZ. And you watch it, you record it, you make a note of what species it is, then you bag the flower again. And then you come back at fruit harvest and see whether it made a fruit or not. And so the percentage of the virgin flowers relative to the number of finished fruit is the fruit set. And so a more efficient pollinator will have a higher fruit set value. It does a better job of pollinating flowers on average. And that's kind of the gold standard of measuring the efficacy. And solitary bees, hands down, just blow away honeybees on single visit fruit set. You know, they're much more efficacious. They do this in part because they probe the flowers much more aggressively. I mean, they'll get in there and just really buzzing and digging and trying to get pollen, and whereas a honeybee's just kind of doop-a-doop-a-doop-a-doop-a-doop. Oh, there's a squash flower. Do-do-do-do-do-do-do. Hello. Let me. I don't really like you. I'm going to go on to this other. Doop-a-doop-a-doop. Watch them. You know, they're just sort of laissez-faire foragers. Whereas the cucurbit bee, the eastern cucurbit bee, God Almighty, you watch them and it's like a laser beam. Zoom, 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 zoom. And every flower they're at is. Yeah, that's one of the things they do. In the case of bumblebees, they will sonicate the flowers. They will, on a blueberry, we grow blueberries in my state, and so the bumblebees will get on it, and you can hear them. And they also, you grow nandina bushes, ornamentals. You can hear nandinas, bumblebees on nandinas do the same thing. You can hear them in your backyard. These little bursts of wing vibrations, and that's making the flower release its pollen, and it rains down on them, and they can collect it and spread it around more easily. So honeybees don't do any of that. Honeybees don't have those specialized behaviors. It's again, because they're social, they don't have to be efficient. It's like, yeah, why bother? You know, I'll get around. There's going to be something better blooming next week, so I'll just deal with it. So there's advantages and disadvantages to being social when it comes to pollination. I'll talk about that a little bit more too in a minute. So anyway, when you add up the interactions of the plant's genetic necessity for cross-pollination and its flower morphology and its acreage and its economic value, you get figures like this. What is the economic value of biotic pollinators? And I can report we have a new value dated from 2021 for Georgia. We have, and also for the states. So in Georgia, we know from 2021 that about $488 million a year can be attributed to all biotic pollinators. That figure in the United States, also from 2021, is $34 billion. This paper right down here that I'm citing, this is from Penn State, by the way. This Jordan is the author at Penn State. They have a county map that I'm going to show you here in a second, and they show that 20% of the counties in the country produce 80% of all that pollinated value. So this is very clumped in its distribution nationally. And then we have a value for watermelons in New Jersey, Pennsylvania, a joint study between Rutgers and Penn State, where they laid the value at honeybees at about 1.3 million and the native bees at 2.25 million. So native bees here are adding more, net value to watermelon production in these two states than honeybees. And these guys tend to be wild, with the exception of orchard crops and greenhouse tomatoes. and upper Midwest alfalfa. Virtually all wild bee pollination is, well, just that. It's wild bees. And rather than managing them, we're trying to conserve wild lands to support their numbers. Here's that county map. Check out your county. Kind of shows you where all the value of pollination is coming from. The Midwest is pretty strongly represented in the clovers and sunflowers. Here we have the soybean belt going on right here. Even though soybean is self-fruitful, it still gets a significant bump from bee pollination. But of course, the real tail that wags the dog is the West Coast, isn't it? I mean, this is where all the heavy hitting is happening. So not at all a uniform map, which kind of feeds the confusion that's out there too. Well, how valuable is pollination? Oh, human life would be impossible without pollination. That's not true. That's really not true, because we could survive quite well on cereals and wind-pollinated crops or vegetative crops. But when it comes to pollinated crops, we really need the biotic pollinators. That's not trivial. It's not just a matter of luxury. The pollinated crops also tend to have a higher fraction of vitamins and minerals than the vegetative crops. So that's important in a global scale in trying to promote human health and well-being, especially in developing countries where they have such a small fraction of their diet dedicated to pollinated crops. And that's something I think, if any of you are all interested in human justice, that this is an area that our discipline really interfaces with the quality of life around the world. How can we increase the amount of pollinated crops in everybody's diet, not just the privileged countries? So minerals and vitamins are stronger in fruits compared to the vegetative part of a plant, because the plant's investing more energy in the ovary. And that's what the fruit is. The fruit is the ovary. And the plant pours a lot of energy to that ovary to make it big, to make it succulent, to make it sweet. And why make it sweet? So it's palatable, so that vertebrates eat it and spread its seeds. And so this is all part of the strategy, but it's expensive for the plant to produce that fruit. And so for all these reasons, we see it downstreams to make it more expensive for human consumers as well. So good pollination helps increase the availability of these high-quality fruits, and it also has a land conservation effect. Because if I'm increasing the output of my available acreages, that's a disincentive to keep taking land out of nature and into agricultural production. So good pollination is good for land conservation and habitat preservation as well. So it's a bountiful basket of benefits to promote good pollinators. Now back to that study from Georgia. I'm going to tell you this because it's a general principle that applies to Texas as well. What you're seeing here on the left is the crops in Georgia and their contribution to that figure I told you, 438 million. And in Georgia, the top three are blueberries, watermelon, and cucumbers. And then it kind of trickles out down here. Apples are fairly low, pumpkins low, blackberries, maters, and so forth. Now I want to explain where this comes from. And that's partly explained by this graph on the right. This is that crop's pollinator dependence, which is a value we can assign between 0 and 1. And this is the fraction of yield that is dependent on crossing. The bigger that number, the more that crop needs to be cross-pollinated. Now notice how it's not an exact correspondence with this graph over here, because this value must be multiplied with the acreage of the crop and then multiplied by the farm gate value of the crop to come up with this value. So it's a product of three values. The pollinator dependence times the acreage times the farm gate value gives you the economic dollars and cents value that goes into these estimates of pollination. But that pollinator dependence is the beginning of it all. And that's why, for example, squash has a really, really high pollinator dependence value. I'm sorry, that's strawberries. A very high pollinator dependence value, but it's relatively low acreage in Georgia, so that's why the value for strawberries is pretty small. So just be aware of these dynamics. It's not straightforward. It is a dynamic that goes into answering these kind of questions. How valuable are pollinators? Another thing that goes into it is the ease by which the flower can be pollinated. There's different morphological types of flowers that result in different fruits. Let's kind of go through 4 of them here. What is a berry? We toss that word around a lot. My high school mascot, I swear to God, I didn't know it was weird until I went off to college. But I grew up in Logansport, Indiana, and there is a loganberry that is grown up there, and my high school mascot was the Logansport Berries. And I remember just taking ridicule from the other team, squash the berries, that kind of stuff. I thought, what's the deal here? It wasn't until I went to college that I realized how weird a name that was. So anyway, the berries. What is a berry? Well, a berry, by definition, is just simply a fleshy fruit without any interior core that has multiple seeds. So that satisfies a tomato is a berry. A watermelon is a berry. Bananas are berries. So you see, it's not just the kind of berry that you think. Blueberry is a berry, but it is a strange exception in which the actual fruit does not evolve from the ovary of the blueberry. It evolves from the green tissue surrounding the ovary. So it's called a pseudoberry. I know that's going far too much in the weeds, but I thought that was just so weird I had to say it. So, but the point is, a berry is not necessarily the easiest kind of flower. It's got this stigma on the tip, and the size of the berry that results is almost always positively related with the number of seeds or the number of ovules that get fertilized. The more ovules get fertilized, the bigger the fruit. The more ovules, each ovule requires a pollen grain. So you got to have a lot of pollen deposited on the stigma to get a good berry fruit pollinated. Okay, let's move over now to the drupes. The drupes, by definition, are a fleshy fruit with a hard stone in the middle with a seed inside the stone. And this includes the archetype, the peach. The peach is the perfect example of a drupe. Almonds are drupes. Blackberries and raspberries, each one of the little individual nubs on one of those is a druplet. Okay, because they satisfy that criterion. Got a hard little crunchy seed with the actual real seed inside it. A drupe. A drupe is fairly easy to pollinate. It only has that one seed, so it only needs one grain of pollen, in theory. In reality, you like to have more than that, just as insurance. And they like to see about 10 to 12 grains of pollen on an almond flower, for example. But you really only need one of them to viably germinate and pollinate the seed. So drupe is kind of easy. A pome is an apple, and this is a fleshy fruit with many compartmentalized chambers in the center. And here we have the apple. And most of these pomes have a 5-branched stigma, each one of which needs to be pollinated. So it's a little bit harder now. The pollinator has to visit and deposit pollen on each one of those 5 stigmas if you want to have a large, symmetrical, fully formed fruit. The hardest of all are the aggregate flowers. The aggregate flowers are not just one flower, they are a mass of many flowers. And in the case of strawberry, each one of these little seeds that you see on the surface is the apex of its own little private pistil. So it's one flower masses a whole bunch of the female parts of the flower into one concentrated clump and then puts one corolla over it. So you see what they've done? They've just brought in a bunch of females, massed them together, maybe given them some anthers, and then put them a whorl around it, so it's a compound flower. Sunflowers are like that too. Sunflowers, each one of those a little individual floret massed onto one head. These are the hardest to pollinate, kind of for obvious reasons. The pollinator has a lot more work to do. It's a rare pollinator that can pollinate an aggregate flower with one visit. It usually takes many successive visits to get a fully pollinated, symmetrical strawberry or sunflower head. Okay, we've seen this. This is some of the interior nests, some of the nesting materials that some of the solitary bees use. This is a cane nesting species, probably a mason bee, because she's made her partitions out of mud. They will partition, lay an egg, make a ball of pollen, lay an egg on it, another partition in linear succession. This is a carpenter bee. You don't have them, do you? Guys that burrow around in your patio. Well, they use cardboard. That's why they're always chewing on your deck, because they make cardboard and separate their cells with cardboard. But it's the same thing. Leafcutter bee, see those nice pretty green leaves of alfalfa that they make into individual cells? This is a carder bee, but this pattern gets repeated in 100 different varieties. This is one of the archetype soil nesting bees in North America, and that's the alkali bee, which is a natural soil nesting bee of the Pacific Northwest, and it's a great pollinator of alfalfa. It's a native bee pollinating alfalfa with a high degree of efficacy, and it occurs in these huge nesting beds that my colleague Jim Kane was gracious to provide me this photograph of a typical alkali bee habitat in Nevada. The soils in that part of the country are alkaline on the surface, and it makes this hard, crusty surface to it, and the bees love that, and they will penetrate and make their little nests in that substrate, and they do a good job of pollinating. And this leads me to something about the use of solitary bees for pollination. They don't like to fly very far. They're kind of like people. They're not going to fly any further than they have to. These are 3 species in their average flight distance. And their distance they will fly is, let's take a look at this graph here to the right. It's an effect of distance, yes, but it's also an effect of the quality of the patch. Will they go 200 meters for a really, really rich patch in preference to 50 meters for a mediocre patch? You know, what do? Well, it kind of depends on the calories. You know, they're really good at monitoring this. They can monitor and self-appraise the calories that they are gaining and figure out whether it's worth it or not. And if it's more profitable to go the 200 acres for a really good resource, they'll do it. But if they can get it with a source in 50 meters, they'll do it. Whichever of those options gives the optimum income. And ecologists have tracked this, and it's unfailing. Okay, it never fails. It's one of the most rigorous laws in biology. You know, biology is a squishy science, but this one is repeatable over and over. Animals always find that sweet spot. So you see here that the line kind of bends downward with distance as long as the patch quality is getting better, and they're really good at discovering these optima. But on average, we like to see about 300 meters seems to play out across most crops and systems as the upper limit. They're going to forage within 300 meters from their nest. So back to Jim Kane's picture. If you have a little bed of alkali bees right there, you can expect them to forage on average about 300 meters within that cone. And they're going to do a very good job at it. And they're going to, because they're solitaries and because they're specialists, they're going to do a fantastic job. Now you could instead bring in a couple pallets of bees, honeybees. And what are they going to do? They'll do something like that. Because they're A, social, and they have a big food supply, so they can afford this long, lengthy foraging trip, and B, they recruit one another, and so they're out there scouting, looking for the best thing out there, which is fantastic as long as it's your crop. But what if it's that wild weed? Or what if it's that wild weed? So solitaries are really, really good because they will only go about 300 meters. So you don't really want a bee that's out there sampling the whole landscape. But, you know, if the stars and planets line up good and the crop is really attractive to the honeybees, they'll do a great job. So you see how situational all of these kind of conversations are? There's been a lot of work in the last 20 years with solitary bees to figure out what kind of habitat do you need and how near does that wild habitat need to be to your crop, to cultivated lands. And one of the biggest things that's emerging is you don't want a homogeneous monoculture that's a simplified landscape. You want a complicated landscape with lots of edges, lots of islands. And Claire Bremen at UC Davis, she's actually worked up some estimates here on watermelon growers that if they have, you know, greater than 40% natural habitat or greater than 30% habitat within these radius of the crop, then the grower does not need supplemental honeybees. And she has shown this with a high degree of repeatability. So this is really practical if you're a watermelon grower, to go out there and just Google Map and get an analysis from the crop and soils division and what kind of wild lands you have surrounding your crop, and figure out the distances to your crop. Then this lets growers make decisions of whether they even need to import honeybees or not. And I think we're going to see more and more research like this happening as we recognize more and more the value of our native non-managed pollinators. I want to conclude by giving you some stories of out there in the literature of complementarity. And probably the best paper that first came out in the early 90s was this one that talked about strawberries, that complicated flower that strawberries have. And they were able to show that honeybees, this is a paper that came out in Ontario, that honeybees tended to predominate on the apex of the flower. And so they were really good at pollinating the tip of the strawberry. But it was your small wild bees that predominated at the middle of the flower and the base of the flower. And so from the early 90s, we knew that multiple species visits to one flower had a better possibility of making a big, fully pollinated, symmetrical strawberry. We know that similar complementarity happens in apples. This is a paper that was published out of Europe where they were able to show that when there's bumblebees and honeybees, both in an apple orchard, it increases the cross-pollination efficacy of the honeybees. And here's what happens. The honeybees, you want them to cross rows, because apple growers and blueberry growers, for that matter, they interplant pollinizer varieties so that they will cross-pollinate one another. Well, it stands to reason you want them to not just go right down the same row, you want them to cross over, and pollinate, the next aisle over. Well, when honeybees are out foraging and when they encounter a bumblebee, it agitates them, the honeybee, and she flies off in a huff. I know I'm anthropomorphizing, but I can get away with that with this crowd, right? And they fly away. They leave and they go over to the next row. It bothers them to encounter another competitor out in the field. So this is good, right? It bumps them over to the next aisle, so it increases the possibility of cross-pollination. This has been shown not just once, but multiple times. Here's another paper. Jeff Pettis, formerly at USDA, came out with this back in 2013. And this is looking at honeybee performance in the presence of non-honeybees with or without them. And this is looking at the proportion of movement across rows. And this is the pollination effectiveness. And this was with non-apis bees, not just bumblebees, but other wild bees. If there's other wild bees in the orchard, the honeybees cross rows more frequently. This is good. This is a paper looking at the same thing with bumblebees in cherries, and this is from Germany. And here, as the bumblebee abundance increased, the honeybee row change probability increased. So it's, what is that now, 3 different crops where this principle has been shown. It's agitating, it's disruptive, and that's good for honeybee pollination. You want them a little bit agitated and moving around in the field. Strawberries. Claire Craman worked on this. She was simply looking at the presence or absence of wild honeybees, or wild bees versus honeybee pollination efficiency. And in both of these measures, as wild bee richness, species groups, and wild bee abundance, bees per meter, as both of those values went up, the honeybee pollination efficiency increased. Wild bee abundance is simply their number. You go out there and count individuals, 1, 2, 3, 4, 5. Species richness is the number of different bee species you go out there and count. So slightly different. And in both of those going up, honeybee efficiency went up. Why? She hypothesized that the solitary bees, because they're such good flower visitors, they loosen the pollen, they make it available on the flower so that when the generalist honeybee comes around, she just picks it up sort of accidentally. Honeybees are kind of like the cargo carriers. There's just so many of them, but the solitary bees are churning up the pollen and making it available for the honeybees. Blueberries, this has been my area of work. We have lots of blueberry culture in in Georgia, and a lot of carpenter bees that notoriously rob the flowers. They pierce the base of the flower and they leave these wounds in the side of the flower that then honeybees come around to, and then the honeybees become secondary nectar thieves. And so we were interested in a former student of mine. We were interested in how this robbing behavior may affect the pollination outcome in blueberry. And my students set up these different tents with honeybees, with carpenter bees, with honeybees alone, with carpenter bees alone, every possible combination. And we showed that illegitimate honeybee visits do in fact increase as the time goes on and there's more and more nectar thievery holes. We were also able to show that honeybees, in the presence of Xylocopa, they pollinate quite well, but when Xylocopa was by itself, they got pretty bad pollination. But that very same year, later in the year, another paper was published in the same journal that was aware of our study, and they looked at it again, and they made this observation, that our observations demonstrate that male carpenter bees are benign or even potentially beneficial floral visitors of rabbit-eye blueberry. Their robbery of blueberry may attract more honeybees to the crop. So we have a couple different interpretations here, and you can kind of see what you're seeing right here from their results. This is the Xylocopa by itself, the carpenter bees, and this bar right here is the Xylocopa plus honeybees. And the presence of the Xylocopa in Mississippi increased the pollen deposition by honeybees. I love it when results differ. It just kind of shows you how the world's complicated. The most recent study I know is also about blueberries. This comes out of Maine. My colleague Frank Drummond, who just recently retired, but he was able to show that the order in which a bee visitor visited the blueberry flower had effects on its subsequent fruit set. So what you're seeing here is the first visitor and then the second visitor, whether it was a bumblebee, or a honeybee, or honeybee, bumblebee, honeybee. And he was able to show that bumblebees, first of all, are by far the more efficient pollinator, but honeybee efficacy was improved when it was subsequently visiting the flower that a bumblebee had visited. And again, the hypothesis was the same. The sonicating bumblebee liberated the pollen, and then the honeybee helped freight it away. A lot of stuff here, isn't it? If you're interested in this kind of thing, I alert you to my book that just came out last summer, Crop Pollination by Bees. Let me warn any of you authors out there, beware of putting the words Volume 1 on your title. That rather commits you, doesn't it? And so the publisher's still saying, Keith, Volume 2, Keith? It's coming, I promise you, it's coming. Let me summarize what I had to say for you this afternoon. Pollination and pollinator value are highly crop and habitat specific. I didn't really talk about central place foraging theory, but that's just simply a fancy way of saying that bees have a home. They are like us. They have a place that they go home to at night, and so their foraging has to take into account the calories to go out to work. Just like you, if you commute, you have to take into account the time spent commuting. Is it worth it going to your job? Is the commute worth it? And they're just simply asking the same question with calories instead of dollars. But it still has to be weighed in to their foraging ecology. Foraging distance is regulated by the life history, whether it's solitary or social, body size, energy budgets. Foragers are always going to optimize caloric gain and expenditure. They're unflappable. They always hit it right. The nearness of semi-natural habitat increases wild bee abundance and species richness, and pollinator diversity improves the efficiency of the honeybees. So I think this is good for us to know, those of us who work in pollination and we traffic in honeybees, we will hear these kind of questions. Hey, should I keep using your bees? Because I've heard that, southeastern blueberry bees are better pollinators of blueberries. So it helps us answer them, to have knowledge and ready facts that we can present. So I think I'm out of time. I think we are out of time. So thank you for coming and listening to me.